discuss some HPLC technology that is of interest to you all, and learn a few things about the way the market is aiming at this moment in time, and where we're moving things forward. So in terms of general pharmaceutical analysis, whether you're at the beginning of the drug discovery process, or whether you're further along the line, lead generation, lead optimization, heading into clinical trials, HPLC and HPLC columns are used throughout that whole process, from initial discovery and looking for targets, all the way through to the launch of a new molecular entity onto the marketplace. So, HPLC is pervasive throughout that whole process. So we use an awful lot of HPLC columns. When I discuss this with customers, they're always discussing productivity with me. My goal is to be more productive. My goal is to speed up my analysis. Can I go quicker? Can I still have resolution between my critical pairs? So there's several ways we can increase the speed of analysis. We'll briefly touch on those. But the main emphasis of this presentation today is that even if we're trying to speed up our analysis, can we do this whilst maintaining resolution? Because if we don't maintain the full resolution between all our peaks, then going faster is not really gaining us anything. We cannot miss an impurity or lose a peak amongst other peaks just because we want to go faster and faster. So you have some compromises. We're going to talk about resolution in terms of new stationary phases built onto a new silica template, and what that actually achieves for you. So if we look at the resolution equation, there are three main factors to the resolution equation. The first of those is gaining retention of our analyte species, our unknown compound. And that is our K prime. K prime, we normally operate somewhere between about 2 and 10 as saying that this is a very accurate region. Once you get past 10 for K prime, then you gain nothing by retaining that compound longer and longer. It will not give you more resolution, it won't give you more selectivity. So we work in this 2 to 10 region for K prime. And if we're there, we know that we have some accuracy. The second part to the equation is efficiency. And you can see the blue line for the efficiency curve. This increases as we lower the particle size. And you've been doing this for many years. We moved 20 years ago from 10 micron particles down to 5 micron particles. We then moved down to 3 micron particles. We moved to 2.5 micron particles. We moved to 1.7 micron particles, which is generally where the technology in terms of lowest particle sizes has stopped for the time being. And you can see that efficiency, as we keep moving down in particle size, keeps increasing. So that's a factor that we can use in determining the resolution and selectivity between our peaks and increasing the values. But you'll also note that selectivity, the red line, has the strongest influence on the resolution between our peaks. So the selectivity mostly comes from our stationary phase. And that's why today we're going to talk about a few new stationary phases in terms of the selectivity that they provide, but combine that with an increase in efficiency based on a new type of silica particle. So when we choose a column, so we're looking for selectivity, we're starting our method development, most people would tell me that they choose a C18 column as their first starting place. Where do you go from then if C18 doesn't work? So C18 is a hydrophobic mechanism. That is how it's retaining our compounds, our analytes. Most people tend to turn around and say, well, the next column choice that I pick is a C8 column. The problem with doing this is that C8 is also a hydrophobic mechanism. So you are not really changing the selectivity term. Therefore, you won't really gain much more resolution by moving from a C18 to a C8 if you're doing method development. What we should be doing is moving to alternate orthogonal selectivities. So things like C18 with polar end caps, so that we add a second mechanism into the equation. So we still have the hydrophobicity of our C18 ligand, but we also have polar end capping to provide us with a second mechanism for interaction, so that more polar compounds or compounds that just have some polarity will hopefully retain strongly and give us a different type of selectivity. Another option that we've looked at in the past is phenyl. So adding an aromatic character, a dipole charge, to the ligand gives us again a chance to change the selectivity. So we're going to look at some selectivities that offer you the best combination of these types of stationary phase and how you can actually use them in your method developed screening in order to start your analysis with the best chance of gaining resolution between the peaks of interest. So we're going to look at a few of these phase chemistries here, and what you will note straight away is that there's some combination stationary phases there. So the first one is a mixed C18 and PFP, so pentafluoryl phenyl. The second stationary phase is a C18 mixed with an aromatic functionality. So we're instantly adding in alternate selectivity to C18 columns in order to gain the selectivity and the resolution that we require. And then we can add in various different functionalities after that. So phenyl hexyl chemistries, diphenyl chemistries, RPamides, where you have the potential for a positive charge, depending on the pH that you choose for your mobile phase. So that can give us, again, some interesting movement between peaks to gain selectivity and resolution. Just to take a step back slightly to efficiency alone before we move on to resolution, when you've been provided silica particles in the past, the image on the left is quite a good representation of what happens within the column. So when you have a 5 micron particle column from any manufacturer, what you actually have is an average of 5 micron particles, and you have a Gaussian distribution, which also means that you will have some 4.5 micron particles, some 5.5 micron particles. So these are a relatively large spread of particle size with an average of 5 micron. So that gives you an efficiency somewhere in the region of about 80,000 plates. And that's what we've been using for the last 10 or 15 years, generally when we've been packing and making silica-based columns. What I want to talk to you first about is a new monodisperse, fully porous particle. So the image on the right is showing you how these particles are now all much more even in their distribution of particle size, so that when you're using a 5 micron column, it's much tighter Gaussian distribution of these particles. What that means to us is that we increase efficiency. So if we look at the numbers that we would gain, here we've taken 2 standard 3 micron commercial columns that are available in the marketplace. And you can see this Gaussian distribution where you have an average somewhere around 3 micron, but you also have sub 2 micron particles. You also have 3.5, even up to 4 micron particles in these columns. So that gives us the level of efficiency that we've always had. But can we improve that? Because if we can improve it and we can improve the efficiency of the column, then you saw from the resolution equation that increasing efficiency gave us more resolution, more selectivity between our compounds. So you can see from the red peak that this Gaussian distribution has now been tightened up an awful lot on the EVOSPHERE particles. So now when we say this is 3 micron, it really is a lot closer to being all 3 micron rather than a much wider spread of particle diversity. If you look at the actual numbers, there are multiple ways of measuring this. So I've shown 2 ways of doing this. One of them is by Coulter counter measurement. So that's measures D9010 of that Gaussian distribution peak. The other way of measuring these particles is to physically look at them under SEM. And again, you can see that, you get very slightly different results between measuring them on a Coulter counter or measuring them by SEM. But the important factor that comes out of this is that the 2 commercial 3 micron silicas that I've labeled as A and B both have a D9010. So that's the spread between the largest particles and the smallest particles at 90% and 10%. And that gives us a value somewhere around 1.6. So that proves that, there is this spread of particle sizes. The closer we get to 1, the more monodisperse our particles have become. So therefore, 3 micron being truly 3 micron particles with not much other sizes available in there. You can see on the monodispersed EVOSPHERE particles that we now have a D9010 down at 1.1. So this is showing and proving that we have this very tight dispersion on the particles. And what that means to you as an analyst in your laboratory is that if we compare these monodispersed particles to standard commercial particles in the marketplace, for 5 micron, we gain 50% efficiency at least. And on some compounds and in some mobile phases, we will gain even more. For the 3 micron, we gain over 65% efficiency. So very big gains in efficiency just by using these monodispersed, fully porous particles. So you're not having to change anything in terms of the method. You're still using a 5 micron or a 3 micron particle, but because it's now monodispersed, you will see very big efficiency gains. When you do that in actual chromatographic terms, you can see here an example of a 3 micron commercial C18 giving us, averages of 109, 192,000 plates for our peaks that we're analyzing. The 3 micron EVOSPHERE increases those values up into the 150,000s, and we have 161,000 plates per meter for the 4th peak in this analysis. So you're seeing this 50-60% gain in efficiency by just moving to monodispersed, fully porous particles. So we will automatically increase the resolution of our system by using these monodispersed particles. So that's a big gain in terms of the resolution equation for us when we're trying to analyze our analytes. In terms of hydrophobicity, how do these phases sit? So this is a graph of many of the most popular C18s on the marketplace. There is a combination of some of the core shell materials, so speed core C18 is a core shell, some very old ODS stationary phases, so the HPLC ODS stationary phase is probably 25-30 years old, but you can see in general that there's a vast spread of the hydrophobicity, even though all of these phases are classed as C18 columns. What I've highlighted is that even using this mixed combination of C18 PFP and C18 AR that we're going to talk about, you don't lose anything in terms of the hydrophobicity of the system. So it's very strong hydrophobic nature. And this is one of the advantages on these monodispersed particles that you have over core shell as well. Core shell over the last 5 to 10 years has been very popular in terms of method development because it increases the speed of our analysis. Your analyte is only passing through the outer shell of the silica particle. So you get a very fast dispersion process, gives you very sharp peak shapes and very high speed analysis. One of the problems, though, is that you can't then take your method to scale up. So if you are passing on your method from that initial R&D, can I gain resolution between all my peaks? Can I find all my peaks? To people in the next department who want to do prep scale, you see that the core shells don't load up because of the very low surface area that they have by just utilizing the outer shell. So if you lose the efficiency because of the loadability of these, either by mass or by volume overload, then obviously you will lose the resolution between your peaks very quickly. Because the EVOSPHERE is a monodispersed silica-based particle, fully porous, as we've always used for the past 20 or 30 years, it still has a very high 350 meters squared per gram surface area. So that means that the loadability is still very high. So if you develop this in analytical, you can still scale up to prep and not lose resolution because you're not losing efficiency. One of the reasons is because the way these particles will pack into a HPLC column. So I've shown you two columns here. The first one at the bottom shows you where you have that variety of particle sizes. So, this can be a 5 micron column, but as we've already seen, there will be some diversity in the particle size. So 4.5, 5.5 micron particles. Your eddy diffusion, your flow through the column, means that your bands that are coming out, so your peaks that are exiting the column, will be slightly resolved from each other, but will be fairly broad. So this is what you see as either a tailing peak or a broad peak, which then is correlating with the next impurity or analyte in your test mixture. If we have the monodispersed particle sizes, so the column packed at the top, the eddy diffusion is lowered very significantly. And what this means is that your bands, your peaks, your analytes that are exiting the column will be not only much better resolved, but will be also much sharper. And therefore you're seeing these efficiency numbers. So you're seeing the 50-60% gain over traditional 5 or 3 micron particles. And it's due to the dispersion that's happening in the column. There are 3 components to dispersion. One is how long does your analyte spend in the mobile phase, term A? Can your analyte pass into the pore structure, so term B? And how long does your analyte spend within the pore structure, so the term C? So core shell particles largely worked on the C term, the mass transfer in and out of the pore structure, and how long they spent was much shorter than normal because these weren't fully porous particles. But because they weren't fully porous particles, the surface area is very low, you lose loadability, and therefore you have a problem when you want to scale up your methods. These monodispersed particles are now significantly impacting the A term, the eddy diffusion through the column. Because they're monodispersed, the flow path is a lot better for your analytes and for your mobile phase, and therefore you don't lose the loadability and scaling, but you do gain these very, very high efficiencies. So if you plot them on a Van Diemter curve, you can plot core shells against the EVOSPHERE particles and see that you can use these particles at much higher flow rates, exactly the same as we have been trying on core shells for the last 5 or 10 years. If we can keep increasing the flow rate, it means that we can increase the speed of our analysis. So this is also where having this monodispersity, having these very well-packed HPLC columns comes into the forefront of we gain a lot of efficiency, but we can also gain speed by keep increasing the flow rate. If you try this on a 3 micron traditional particle, what happens is that you very quickly lose efficiency because you cannot use the higher flow rates and still retain the efficiency of the system. The traditional 3 micron fully porous particles will not allow you to use higher flow rates to gain speed. Your compromise will be losing efficiency very, very quickly. So we're in a position now with monodispersed particles where it's right at the forefront of particle technology. Now what can we do in terms of the selectivity gains? So I showed you this list earlier. We can add some new and unique selectivities onto these particles and therefore hope to gain selectivity, which you saw was, the strongest term within the resolution equation. So we've already increased efficiency by moving to a monodispersed particle. Now can we add a lot of selectivity to those monodispersed particles by using some of these stationary phases to gain retention and selectivity of some of our more complex components. So if you look at an RPA-mide structure, you will see that you still have a C18 chain, so we will still have hydrophobicity. However, what's built into that chain is an amide functionality. What this means is that at certain mobile phase pHs, you can potentially have a positive charge. If you have a positive charge, you can use that to gain selectivity. So you still have hydrophobicity, you still gain retention of your compounds, but you also gain selectivity. The other advantage that can come from having this positive charge on the stationary phase is also that for basic analytes, you can gain much better peak shapes. You sharpen up the peak shape, which is always a bonus when we're trying to speed up our analysis, but retain the resolution between the compounds. Because if we have peak shapes in the region of 1.3, 1.4, 1.5, the compounds start to blend into each other just based on the poor peak shape that we're seeing. If we have very sharp peak shapes, 1, 1.1, then we can keep increasing the speed of our analysis without losing resolution between the compounds based on the fact that they're tailing into each other. So that's another gain in terms of selectivity and peak shape for basic analytes. The C18 PFP is again largely based on C18 functionality on the surface of the particle, the monodispersed particle, but also now with PFP end caps. So this allows us multiple interactions. We still have the hydrophobic nature of this being a C18 ligand. We have pi-pi interactions coming from the fluorine dipole moments on the PFP functionality. And we can also gain shape selectivity. So we have three potential mechanisms helping us gain resolution between our peaks of interest. So it allows you to use simple mobile phases, and most of the mobile phases that we use these days are things like formic acid or ammonium acetate or just water methanol or water acetonitrile, because we're trying to make more and more of our methods mass spec friendly as more and more customers are buying mass spec and moving slightly away from UV. In terms of being able to, analyze their compounds and know exactly which compound is which without having to inject each individual one. Mass spec is obviously more sensitive and more attuned to seeing those peaks and knowing exactly which peak is which. But the one thing with mass spec where it often falls down is when you have things like isomeric species and you have the same molecular weights between compounds, and that's why you still need the chromatography resolution before you use mass spec as a detector. So we're using simple mobile phases, we're using the complexity of the stationary phase in order to gain the resolution between isomeric metabolite species that you have in your samples. And again, very simple mobile phase here, formic acid in water and methanol, and we have good resolution between these progesterones using the C18 PFP functionality to gain that resolution. The second of the main C18, so both of these are classed as L1 columns as well, the C18 PFP and the C18AR are both in the USP methodologies, is an aromatic functionality. So again, you still have C18 ligands bonded to the surface, but you also have an aromatic phenolic group. And again, this will give you multiple interaction mechanisms with the stationary phase between your analytes to gain the selectivity that you require. And we can take mixtures to prove this using acids, bases, neutral compounds, naphthalene, phenol, obviously relatively neutral, nortriptyline as a basic compound, nalidixic acid as an acid, and sorbic acid as an acid. How does this compare on multiple phases? And can we also use the selectivity of the potential dipole charge? And the simple answer is yes, we can. So if you take that 7-peak test mixture, you can see that on the C18AR, by using either formic acid or ammonium acetate as a buffer, and obviously changing our pH from low pH, somewhere around 2 with the formic acid, to somewhere around 5.5, 6 with the ammonium acetate, that we get different resolution between our peaks. So in particular, peak 1 and 4 move around a lot, and also our peak 6 moves in the opposite direction using pH, which is something that we would potentially expect. 1 and 4 are our acid species, and 6 is our basic species. So they're moving based on the pH of the mobile phase and based on the multiple character of the C18AR stationary phase. And you can compare some of these stationary phases against each other in order to, again, gain differences in resolution and selectivity and retention. So you see on the EVOSPHERE phenyl hexyl column, we get good resolution between our peaks. So nitrobenzene and some of its derivatives. So we have an elution order of 1, 2, and 3. We have strong retention between these peaks. Moving to the EVOSPHERE C18AR, we actually get a switch in the elution order between our compounds. So now they elute in the order 3, 2, and 1. We still have resolution, but we've been able to use a combination of stationary phase to gain very different selectivities between these 3 species. So that's good when we're developing methods on unknown compounds, where we need to figure which of the selectivities is going to work best for us. The C18AR will not always work. So where do we go next? So this is an example where, as a largely predominantly C18 column chemistry, the C18AR, doesn't give us resolution between our analgesic drugs. We move to the EVOSPHERE diphenyl with the same mobile phase, and we get very good resolution between these 2 compounds. So the ibuprofen and the indomethacin. So, this is why we've also put 8 different stationary phases. You can pick combinations of these that give you the best chance. So maybe a C18AR, a diphenyl, and a C12 will show you a method development kit that gives you differences in resolution when you're facing critical pairs in your analysis. And again, things like isomers, metabolites, closely related, are often the compounds that cause us problems. Again, because we have some shape selectivity occurring on the C18AR stationary phase, we get the separation of the hydroxyestradiol on the C18AR that we don't get on a predominantly phenyl-based selectivity. So the phenyl hexyl is a phenyl group at the top of a hexyl chain, which is different to the C18 with the aromatic functionality almost as a secondary end cap. So you're gaining shape selectivity between these compounds on the C18AR that you don't on a standard phenyl-based column. So I said a moment ago, which of these L1 columns would you choose? Well, again, that's a good advantage to have, is that there's multiple choices here. Traditional C18 columns, so your Hypsil Golds, your Fortis C18, your Sunfire C18s, your Luna C18s are predominantly C18 ligand with a hydrophobic end cap. So you only really have one mechanism of interaction, the hydrophobicity, to gain your resolution and selectivity. Here we have 2 choices that are both in the L1 category in the USP, but with those multiple interaction mechanisms. So hydrophobicity, pi-pi, and aromatic, and also some shape selectivity. When a a traditional L1 column doesn't work, which of these do you move to? Well, they're still predominantly C18 phase chemistry. So in some applications, you will still see the same result between the compounds of interest. So here you see that there is very little difference between those two stationary phases, again on a mixture of basic and neutral compounds within our 7-peak mix that we're running here. However, on other test mixtures, so here we have aspirin, paracetamol, and some of the metabolites that are included within those two compounds when they're analyzed. And you see that between the C18AR functionality and the C18PFP selectivity, we can now move some of those peaks around. So in particular, peak 2, peak 7, and peak 10 all move and provide us with alternate selectivity. So these are still L1 columns. When your standard L1 column doesn't work, you now have these multiple mechanisms to pull metabolites, isomers, problem compounds apart from each other and gain more selectivity, more resolution between peaks. Another example where we have an acid, a base, and a neutral compound, showing the difference between the two columns and showing that we do have very different selectivities occurring. So on the C18PFP, peaks 2 and 3, which is the procaine and the phenuron, do not resolve from each other. However, on the C18AR, those two peaks are pulled very nicely apart, and we would use that column as our choice of starting method development. If you have more polar analytes, then one of the phases that we've made, one of the stationary phases, is a C18, but with a polar end cap. So this is the EVOSPHERE Aqua. This can also be used in 100% aqueous mobile phases. So if you're looking at compounds that are very, very polar, so in this case, isoascorbic acid and ascorbic acid, we can run 100% mobile water aqueous mobile phase. So in this case, just formic acid in water, so slight control of the pH, but a water mobile phase. We gain selectivity and resolution between these two metabolites. And we do that even in a simple water mobile phase by utilizing the correct stationary phase to gain polar interaction with those compounds and therefore gain retention and selectivity. And we can do things like nucleosides, nucleotides on this particular column because it has this polarity, because it likes the more polar analytes. So again, predominantly C18, but with a different type of selectivity attached, which means that we can do the more polar analytes on these EVOSPHERE Aqua columns. So remember that you're still gaining high efficiency, you're just adding in the correct selectivity by the correct choice of stationary phase. One of the things that we do as a manufacturer, because we're telling you that these particles will be high efficiency, will be good peak shape, will be good selectivity, is that we fully QC test each column. So the certificate that you get in the box with the column is for that individual column. So it proves to us that we have these 150, 160,000 plates per meter on our 3 micron columns, that we have 120,000 plates on our 5 micron columns. And we also do this in a 1.7 micron particle. So then you are talking plate counts, 180, 200, 230,000 plates per meter, depending on the compounds that you're running. Again, significantly above where we've been in terms of efficiency on 1.7 micron HPLC particles, and then all with these 8 unique selectivities on there. But it means that in terms of robustness and reproducibility, you can be very confident in the performance of the columns because they're individually QC tested. So you have this guaranteed reproducibility not only from batch to batch, but also from column to column, knowing that these columns are fully tested, not that we only test 1 in 10 or 1 in 20 columns from a batch like many of the manufacturers do in the marketplace. So hopefully you've seen some of the advantages that these stationary phase give us. I've also talked a little bit about gaining resolution from our efficiency. So by moving to a monodispersed, fully porous particle, we gain efficiency somewhere in the region of 50 or 60% over what we have traditionally been getting on 5 micron and 3 micron and 1.7 micron particles. Then when we have that efficiency gain and that scalability and that loadability, we can add these unique selectivity stationary phases and gain resolution between our problem compounds, which are often the case, built into one new HPLC column. So hopefully you've seen efficiency gains and selectivity gains by moving forward with these new HPLC columns, and you see that the advantages that can give you within your own methods, within your own laboratories. So hopefully that has been useful. And if there are any questions, we will try and answer them shortly.
Thank you so much, sir. Thank you so much for presenting this very interesting and informative insights on HPLC column chemistry of Fortis. Dear attendees, if you have any questions or clarification regarding the session, you can simply type them up on the Q&A tab showing left side of your screen, and we'll answer the same. We have another 4-5 minutes for Q&A part. So if you have any questions, you can type them on Q&A tab, or you can write to me. You will get a thank you mail after this session, and you can write directly to me for a clarification or question. We'll wait for another 4-5 minutes, sir. Sir, here is one question. What is the advantage of monodisphere dispersed particles compared to core shell or UPLC?
So the advantage compared with core shell will be that loadability. When you want to, develop your method, will work fine on core shell, will work fine on monodisperse. But when you want to take it forward and have scalability and method transfer, then you won't have that with the core shell particles. They don't pack into prep scale, and they have very, very low loadability. So you cannot really transfer that method. You need to redevelop that method. Whereas on the monodisperse, because you have that 350 meters squared per gram surface area, you develop your method and then you can scale it up to prep. You can transfer it and still have loadability, so that you don't have to redevelop that method. And that makes you more productive over time, that you're not having to have multiple methods developed for the same analytes.
Okay, thank you so much for the answer. Sir, there is one more question. Why there is no regular C18? You have other mixed C18 modes. What is the benefit of that?
The benefit is that, for the past 30 or so years, we as manufacturers, all manufacturers, have given you regular C18s, and the market is therefore overloaded with C18 column chemistries. What we have decided to do is to still give you C18, but with built-in alternate selectivity. Because giving you another C18 is not necessarily giving you advantages in terms of gaining resolution and selectivity in your methods. By giving you the alternate C18 PFP, the C18 AR, which the USP still accept are in the L1 category, we're giving you that chance to have alternate selectivity for your methods than just another C18 column chemistry.
Okay, thank you so much for the answer, sir. And here is another question from Sobhan Surendranath. He's asking, as there are a lot of column chemistries are available, but the real challenge we are facing is the reproducibility and durability. So how Fortis is taking care of it?
The reproducibility I touched on a little bit at the end of the slides. The way we're taking care of reproducibility is that we're individually QC testing each and every column, so that certificate in the box is for that column. This is not us packing 20 columns and only testing one of the 20 and saying this batch is okay. We're testing each individual column so that we know that it's the same as the previous column, and it's the same as the previous column before that. So that is how we're moving this forward. It's making more work, obviously, for us in individually testing every column, but it means that, again, you have that faith in reproducibility of column to column, not just batch to batch.
Okay, sir, another question is from Sri Hari. Can you please explain difference between monodisphere and stranded particles?
So the difference is all due to that D9010, that ability to make a much narrower dispersion of the particle sizes. So traditional 3 micron particles that you get from, again, any manufacturer on the planet are really 2.5, 2.6, 2.7, 2.8, 2.93, 3.1, 3.2, all the way up to 3.4, 3.5. The average is 3, the mean is 3. And therefore, that is what's sold as a 3 micron HPLC column. What we're saying now is that the monodispersed EVOSPHERE particle, if we give you 3, is now 2.9, 3, 3.1. So it still has some dispersion of particle character, but it is much, much nicer. And it's where I showed you the numbers of, traditionally we've been working somewhere around 1.6 for the D9010, which means there is this large dispersion. We're now down to 1.1, which means that it's almost perfect dispersion of those particles.
Okay, thank you so much, sir. Thanks for the answer. Sir, here is another question. Which column is best to start the method development for general molecules?
So I would still start on one of the C18s, probably the C18AR, because it will still give you hydrophobicity, but then it will give you that secondary interaction from the aromatic functionality. So the C18AR is probably the first column of choice.
Okay, thank you, sir. Sir, another one is like, what is the best column for mixed polar molecules, and what is best for acids?
Sorry, could you just repeat that one? Best for polar molecules and what is
the best for acids?
For acids?
Yes.
The best for polar molecules would be the EVOSPHERE Aqua, because it has that built-in secondary polarity to retain polar molecules. So if you're struggling for retention, that is the best column. Acids can be run on the majority of those columns. It depends on what your problem with the acid is. Is your problem its peak shape? Is your problem its polarity? Is your problem the retention? Again, the C18AR, the RPamide would be very strong retention for acid species, because it has that potential positive charge. It will retain very strongly anything that's a negatively charged acid. So the Aqua and the AR and the RPamide would be the 3 starting choices for acids and for polars.
Thank you, sir. Sir, one more question. Do you have any high pH columns, or do you have equivalent column to hybrid columns like XBridge, Xterra?
We do have a high pH column. It is not on the EVOSPHERE particle. It is the previous generation Fortis C18 column, and that will handle pH 1 to 11 mobile phases. So that is the column that we would still use there.
Okay. Sir, here is one more question from Subhan. He's asking, I have an experience with a speed core 2.6 micron, which is giving less back pressure than other 3 micron commercial column with same dimension and chemistry. Would like to know the reason.
On a speed core column, the less back pressure again is due to the way that core shell particles pack into a column. They also have less pore structure, so you generate less back pressure by your mobile phase and analytes not being forced into and forced out of such large pore structures.
Thank you so much. Thank you so much for the answer. If you have any questions, you can write to here. Or if you want to know more about Fortis technology column chemistry, then simply write to us at sales@apexprom.com. Or you can simply revert to mail. Thank you mail you will get after the session. We'll reply on same. I think there is no any now. Rupen sir, are you there?
Yes, yes, I'm here.
So can we wait, or like we should like stop it now?
Do we have any more questions? Yeah, I think we can stop it there, I guess. Yeah.
Okay. So thank you all for joining us today. Thank you, Mark sir, for presenting such a insightful session.
Thank you for your time, everybody.